chalk talk that we haven't done for quite some time. And I'm going to switch the input so that you can, let's see if we can actually, wait, no, oh, I see, oh, shoot. Wait, I can't get, wait, which input am I on? Sorry. Input. One last thing for the video conference here, guys. This thing is being weird. Wait, give me a snap. I need to see myself. Oh, there we go. Look at that. It's almost perfect. Can we zoom? Yeah, but that's good enough. That's good enough. All right. Unsupervised learning, sweet CVPR paper of 4 3D morphable model regression. Now, as you can imagine, it's been a while.
Hey,
yes.
Hey, Doug.
Yes, yes.
Do you mind zooming in on the board a little bit and maybe dialing the lights up or something?
Big for this paper or this chalk talk because unfortunately that camera does not seem to be able to zoom. We have a little bit of a failure in terms of, I mean, it's flashing at me. Oh wait, oh, it's zooming.
Here we go.
Dude.
Yeah.
I'm so happy. It used to not zoom, but now it is. But now, hold on. Extra special awesomeness here. Whoa. Well, okay.
Oh, okay.
You can also switch
I know.
see which color shows up better. Green might show up better than red, or red might show up better than red and green.
It's not framed anymore.
Yeah, I know. I went out. Okay. Oh, look at that. But you're going to be really careful. You may need to. There you go.
That's not bad.
That's not bad. Good. Nobody breathe. Nobody breathes. Sick. Second, it is using everything. There's so many cool techniques being used in this paper to do what they're doing. So what are they doing? This paper is called Unsupervised Training for 3D Morphable Model Regression, which doesn't really tell you what's going on. They're looking at a single image of a person, and they're detecting that there's a face in the image, and then trying to suss out, trying to figure out the 3D and texture of that person's face. So one image, 3D model of the person. How is this possible? 5 years ago, I would have said, no, you're stupid. Go out. Go work somewhere else. It's working, and the results they're getting are not bad. It's not perfect. I don't know if we'd use this for feature film, but it's getting close. They're looking at people, and you can spin around it and look at the models that they're generating, and you can see that that is that person recognized. So we're going to go fast. There's a lot of stuff in here, and we're going to sort of walk our way through what their approach is. And I encourage you to look at various details, because some of this stuff I will make mistakes. I don't quite understand some of the loss functions they're doing here. We're going to go a little slow. But in general, this is a pretty amazing paper. So, step one. What are they trying to do? They are trying to have an image of a person sitting at a table, eating lunch. Their hair is going all over the place. And at the very end of it, they want to have a 3D model of this. So here are these polygons. That's my representation of polygons of that person that you can recognize as this person, and hopefully some sort of way of representing the texture on that person so that it looks good. Now, sitting in front of this is 3D, and it even says there, morphable model. And this is actually technology that came out back in the 90s. 1997 or 99. There's a paper written about this, and this is basically blend shapes, right? But it's blend shapes for people, for identity. So what the 3D Morphable model guys did is they got together with cyberware. Remember cyberware, the big laser, cyberware is still around. Big laser scanner, and scanned a ton of people. They put together this big database of people. And then, not exactly how they did this, I didn't fully read the paper. They went through and figured out correspondences between this large database of people and everybody else. So what do I mean by that? Say I have a person, and we've scanned that person. Oh, and neutral poses. Or let's assume we have neutral poses. We'll talk about expressions later. So here's Bob. And then here is Tim. And over here is something, a little crooked face there. This is Doug. All right, we've got 3 different models, and these are 3D models of a person. We've gone through and cyberware scan them, and they have a certain number of polygons. Let's see, they're working with, let's actually tell you how much this is. 5,300. So they're around 53,000 verts, right? And one of the cool things about these is took this large database of people, and they went through and painstakingly said, if I have the tip of the nose on Bob, I know that that is vertex 13,000. And the tip of the nose on Tim is vertex 13,000. And then the tip of the nose on Doug is vertex 13,000. So they have correspondences between each and every one of the vertices in this 3D model for a large number of people in this, because I don't know the actual answer for that, but it's large. There's thousands, I think, of people that they scanned and aligned this way. So that looks like everybody has 3 eyes, but there you go. So kudos to these dudes. In fact, this was actually done a couple of times, and these guys are using a thing called the basal facial model. But basically, they have a way of putting together all these people. So now, we've talked about blend shapes over and over, again, about having the same person in different expressions. And by having the different expressions, you can create any expression for that person just by blending between the shapes of that person in those different expressions. Now we're doing this for identity, right? And even better, this isn't just 3D locations of the vertices, it's plus texture. So the cool thing is, at each and every one of the vertices of these models, because they've done a cyberware scan, they also have an RGB. Right now it's just RGB color for those vertices. So if you have somebody with a darker complexion or a lighter complexion, you can tell the color of their skin and what this person actually looks like. They scanned everybody under diffuse lighting conditions so that there was specular isn't there, but this is not perfect. It's got some lighting baked into this, but in general, you have texture and 3 locations for the faces. So now, with this, assume we have this, we can do a little math. We can say, all right, if that's the case, then if I wanted the shape of a person or the shape of a thing, then this is sort of vague here. Could have an average shape, right? We could take all 1,000. Let's assume this is not the right number, but let's assume that we have 1,000 different people that we've scanned, and we figured out the correspondences between them. You can just run that through, add up all the vertices, divide by 1,000, you can get the average shape. Okay. And then, if I wanted to sort of blend between people, I could do the old trick where we have a weight, the shape of person 1 minus the average shape. So we have average shape, we subtract that out. This is the difference between the shape of person 1 and the average shape, and I could blend that in there. So if I turned on A all the way to 1, I would get the shape of person 1 out of there, right? You do the little math, and the averages cancel out. All you get is that. All we can do, A2, shape of person 2. You see where I'm going with this, average shape. And plus A3, and all the way up to 1,000. That's 3 minus average shape. Da, 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 da. And you've got A's going from 0 to 1 when you go with that, and as long as, and this becomes actually kind of important, as long as you don't sort of squish together too many high values of A's, you can start screwing around with these parameters. You can start saying, hey, I want a little bit of Doug and a little bit of Bob and a little bit of Tim and a little bit of Sally, and then all of a sudden I get a shape of a person that kind of looks like a person, but doesn't look like any of those guys. And then how you change these shapes, you get to explore the sort of space of valid shapes. And if in 1,000 shapes of the people you scanned, you've got a wide variety of people, the thesis is, if we have this, you can generate any shape, any face. And that's a bit of a leap. And in fact, you can kind of see the results of this paper. Is there something in your face that really can't ever be computed by taking 1,000 different people and squishing their shapes together? I don't know. I'm not sure. But that's what this paper is working with, and they're getting pretty awesome results. Now, they don't actually do this. In fact, this is kind of not the way to do it because those A values are a little funky. The Morphable model paper, the 1997 Morphable model paper, doesn't just stop there. They say, no, first of all, that's a lot of data. And second of all, those weights are a little bit more complicated to control. So instead, and we're going to gloss over this a little bit, they do a PCA analysis of those shapes. So remember, what you actually have is shape 1, shape 2, shape 3, shape 4, all the way down to shape 1,000. And each one of these shapes is 53,000 points. You end up with this sort of big, long matrix. And you can do a principal component analysis of this matrix to tell you where the important things are, right? So the idea here is, and the 3D Morphable model guys who created this went into some neat discussion about how you can do this. You can basically say, out of this, if I analyze all these shapes and ask for the features that are most important, first of all, you get the average shape. You get shape average popping out of there. But then you might get a big nose, shape nose, where people in general have this, we can vary between shapes by this nose shape. And I'm glossing over this. And what you're basically doing is rearranging this matrix, which has different person, different person, different person, into a column of average shapes, a column that affects the nose, a column that affects the width of the eyes, the column that affects all these different parameters. You're basically saying, hey, can we throw out the noise, the little fiddly bits that we don't really care about, and compress this down so that when I add up these shapes that I'm discovering here with the principal component analysis, I can really span the space of the shapes that I've scanned. And indeed you can. You don't need to use 1,000 different shapes. You can actually use, and they use 100. No, 199. Yep, 199. So they get 199 shapes that really represent identity. By adding these 199 shapes together, you can create a face that looks like a person. And in fact, way back in 1999, that's exactly what these guys tried to do. These guys were trying to solve the exact same problem that this paper is doing. They were saying, let's look at an image and see if we could fit the values in the weights that are associated with each one of these things so that we could create a shape that looks like what's in the image. And they got some decent results. Nothing as good as what these guys are getting. All right, so just a little bit more math, just to sort of for the rest of this. Now, I was talking about shapes, but there's also approximately is equal to S of S, comma E, and we'll talk about what those guys are, equals, and this is their, that was too long. That's their average shape. Everybody starts with an average shape. Plus PSS WSSS, and this is all these guys. So I should put little hats on top of these. These guys are vectors. This is actually a matrix because it's the 3 columns, and then plus PSS WSSE. Okay. What? This is a matrix of the principal components that I was talking about. This has got the columns of the shapes that we're using to squish together in order to make our person. This is a diagonal matrix of the eigenvalues of these eigenvectors. So when you do the principal component analysis, these are the vectors that represent the shapes that we're adding up together, and these are kind of the weights, the importance of those things. And this is just a diagonal matrix, it doesn't change. These two values come out of the principal component analysis. This is a vector of weights that say how much of each one of the columns do we use. So one of the values in here might correspond to the size of the nose. Another one of the values might conform to the sort of thinness or wideness of the nose, and so on. So this, if we find this question, we can produce the shape of the face, right? We have the average shape, which we've computed, that is constant. These guys we computed from our database. This is the thing we're looking for. How do we put those shapes together so that we can get a 3D avatar of that person? And if those people are smiling when I'm taking their picture, I don't care. I want to create a neutral pose so that when I create their avatar, I can actually get a decent looking thing. I don't want the smile baked into the thing. So they are willfully ignoring the expressions until the end of the paper when they start paying attention to the expressions again. And this is kind of some of the future work that they're working on. All right, so looks like a crazy equation, but it isn't. Average face, easy. And then the various bits and pieces of the face that you're blending between. And there are some constraints in the values of this. You make sure that the weights of those shapes that you're adding together all fall between 0 and 1. There's some identity values there that we want to know about. But also, there's texture. So just like this, there are 53,000 texture values. And well, S is X, Y, and Z for times 53,000. This is RGB times 53,000. And again, just RGB at this point. And so this also has a parameter where we have T. And T is a vector as well. Equals, yeah, wrong, average texture plus WCD and T. So just think about this. I had a matrix of 3D locations of points, and I had one for each 1,000 person I scanned. Well, I also, instead of just swap out, instead of the XYZ location of those points, swap in the RGB color of those points. And now I have 1,000 shapes of what the texture of that person's skin looks like. The color of their eyes is baked in here. All that kind of stuff is in here for these people. We do the same principal component analysis to sort of extract out the important bits of the texture. And now we have a vector of 199, 199 values that they use to blend between these principal components of all these textures that they've scanned, plus the average texture of a person's face, to get the texture of a specific. Does this make sense? It looks mathy scary, but it isn't. It isn't. It's just 100. Think of it as 199 sliders that you're blending between the important parts of how you control the appearance of somebody's color or their shape of their face. Okay, so now we're not done. This is what we're trying to solve for. And if we could, I'm going to draw on one more line and then before I erase all this. If we could find these two things, 199 values of S and 199 values of T, then using the stuff we got from our database, by the way, this database, totally available. You can just download it. Boom. You can take those values and create a 3D model of the person's face with good color values for each vertex. Right? So that's what we're searching for in all this. Right. Cruise along, cruise along. But we're not done. There's more tech to be used. So how do we do this? This is, first of all, it sounds like really cool, but how best to do this? All right, so we're going to talk about their entire pipeline. So of course, this is machine learning. And what we're going to do is train something. And we're going to start off with real images. All right, this is our base thing. So we have a picture of some person right here. There's a big list of real images. We just go to the internet and get pictures of people's faces, or we go out college campus and just photograph people's whatever. We get a lot of faces. That's all we have. Just pictures. That's where this comes into play. We have at our disposal a 3D morphable model that was created in 1999, or well, it was basically done. And we have this thing that we have that was based on 1,000 cyberware scans of people. And we have this thing that, given two sets of 199 values, we can produce an arbitrary face. We have that. That's known. Then we have a bunch of real images of people, various poses, various expressions, various lighting conditions, various everythings. That's it. There's nothing that we have that says that this person should have a 3D model that looks like this. There's no correspondence. If you took a picture of me right now, even though I've been digitized out the wazoo, we discount that. I would not know what my face looks like. I either have to have somebody sculpt my face or scan it or something like that. We don't have that, right? There's no training that will tell us what my face should look like from here. Drat. This is bad news, right? We don't have anything that will really guide us to what the solution is. Or do we? What we also have is a 3D morphable model, right? I'm just going to type 3D morph. And we can take this thing, we're going to put this thing, and we can render it and create synthetic images. All right. So our 3D model, morphable model, has two sets of 199 parameters. Why couldn't I just assign random values to those things? I would get a picture of a person out there, right? So I could actually send into this thing synthetic parameters, synthetic parameters. And this is, if you remember what I wrote, there's S, T, and also the parameters, like lighting and pose and some other things. So how you would basically think of having a 3D morphable model in Unreal. You're screwing around with it and you go, I want to produce a face that looks like this. I'll move the head that looks like this. I'll put a couple of lights there. And you're just moving sliders around and changing the pose. And out of it, Unreal is rendering a 3D face for you in real time. Right? Pose. So I can actually, and now this is the cool thing, is I'm generating images, synthetic images, and images. I have two sets of things. The cool thing about this is I know what the 3D model should look like. Here, what should the 3D model look like? Beats the hell out of me. I don't know. That's what we're trying to solve. Here, I have examples that look like people. They actually really do look like people, but I know what they started from. So I have a correspondence between the image and the 3D model. I'm not going to tell my machine learning I have this. Well, I am, but I'm going to use this to my advantage. But we're going to treat this and this as two sources of images to start training our system. And this is one of the cool things. In fact, we start training the system using the fake stuff first to get it to go. Right? They're starting to use it to sort of figure out the values of the parameters. And then they started introducing the real people. And then they start saying, well, does our system, which was trained with synthetic images, actually create a valid model for a real person? Okay, so how do you do that? So if I create this, send it through my machine learning, and then it's at the end of the machine learning, it spits out a 3D model. I can compare it to the synthetic model, easy peasy. How close is it? I can just measure the distance between the vertices and the textures and all that kind of stuff. How good is it to what it created? But say the first time I throw this at it, I throw a real image at it, it does something and produces a 3D model because it's been trained, it's been jump-started. How do I tell if I'm close? Again, I don't know what the 3D model of this guy should look like. It's just a photograph. Clever idea. There is out there a thing called FaceNet. All right, FaceNet was created by Google, and there are other ones out there. There's VGG Face, I think, of VGG Face. There's other things that are like this. But this thing, FaceNet, can look at your face, an image of your face, doesn't matter, and it tells you that this is a picture of Doug. And the accuracy on FaceNet is stupid. You know, just load something up into Google's image photo depository, and it will identify everybody in the image unbelievably well. And you could be on the beach, you could be at a party, you could be turning your face off to the side. FaceNet is really good. And you can download it. It's on GitHub. Okay. So here's their concept. We have real images. I can take a look at the output of FaceNet. And before it gets to Doug, the output of FaceNet is a list of numbers on a hypersphere. It's basically a hypersphere of identities. I can run FaceNet on the real image, and it will tell me, instead of, don't think of Doug, think of a list of, I think it's around 200 numbers. Let's say, in the world of identity, this is that, and that number just sort of corresponds to Doug. We can also run this real image through our machine learning and create an image, right? We can create a 3D model we can then render. Remember that 3D model comes with shape and texture. And you can take the image that it produces and run it through FaceNet. This is brilliant, right? Because FaceNet looks at an image and tells you, it gives you a sort of unique ID for the identity of that person. And so I'm going to draw a sphere, and this is a stand-in for his twin is actually fairly close to Doug in this hypersphere. And somebody else might be over here. This is Bob over here, and Sally might be over here. So their thought was, I love this thought, run the real image value there. How close are they? The thought is, if they're close, we're good. If we can get this thing to closer, that's even better. So if I can move this little triangle on top of that plus, then what I've just done is created a face that fools FaceNet. And FaceNet is hard to fool. FaceNet is damn good. Google put a lot of work into FaceNet. So let's use that to our advantage. All right? We're going to train this system using synthetic images and real images, so sort of alternating. And we're going to first take this and put it into an identity encoder. And that is FaceNet. right? So this thing is first going to look at our images and produce, I lied. The output of the encoder is the penultimate 1024 dimensional average pool layer of the NN2 FaceNet architecture. Whatever. This thing spits out a 1024 dimensional vector that represents the identity of your person. Then we're going to use this and feed that into our 3D morphable model regressor. And you're saying, what? Wait, what? This is the thing that actually is the brains of our thing. This is something we downloaded from Google, and it spits out 1024. We're not changing this at all. What we're basically doing is encoding the image that we're getting, whether it's from a synthetic image or a real image, into an identity. Because this is all about extracting an identity, and then trying to figure out, instead of taking an image to a morphable model, I want to take these 1024 values and turn it into my shape. So the output of this is a 3D shape, right? So there is a 3D shape with textures. All right? Now, initially, this will start up horribly. We don't know how this works. We don't know how this thing is actually going to be able to do this. And this 3D shape with textures, remember, that is being represented by S and T, right? Because this is all working towards our 3D morphable model. So remember how I said at the beginning, we're going to start off and just start training based on this? Well, we can. With this right now, we can stop and put in a parameter loss. So say we're just starting this off, and we want to get this to go, and we want our 3D morphable model regressor to start producing 3D shapes that are kind of like the image. But we start with synthetic images that we generate from synthetic parameters, randomly chosen. Send it into the identity encoder. It produces a number that represents what that thing thinks you look like. We send that to our morphable model regressor, which is a convolutional neural net. Yep, I think so. And then, I'm not even sure. Well, they do talk about it, but convolutional neural net. Let's assume that, but that might be wrong. And then this produces S and T, which we then can compare against the parameters that we started with. And we can try one little machine learning thing. Remember machine learning, where you throw in there, and if the results are off, you change the parameters of this thing so that the next time you throw an image in, it works a little bit better. And we do this over and over and over again. We do this for a bazillion synthetic images, but not too many, because you don't want to train it so that it just recognizes synthetic images. You're basically using this to jumpstart. So then you're going to start showing some real images to this, but you can't follow this path, right? Because there's nothing to compare. There's no parameters that go with this. We don't know that. So we add, and I love this word. This just so cool. Differentiable renderer. Before we get to the word differentiable, let's think about this. This is just taking this 3D shape and texture and producing an image. This is just a renderer, right? So this is going to create a 3D render, and it doesn't render hair or anything. It just renders the face that went into this. So this takes our 3D shape and creates an image out of it. All right? So once we have an image, what can we do with it? Well, we can send it into FaceNet. Remember, I said we were going to be comparing these two things. So now, what pops out of this? A 1,204 dimensional vector that represents the identity of the thing that just got rendered. Okay, so we're going to stop right there. There are a couple, well, there's a couple of different loss functions. I'm actually going through this paper faster than I expected. There are 3 different loss passes that we're going to show up here. But let's start with the one that I've been talking about the most, which is the comparison of these 2 values, right? So at this, I wish I had $1 million. Multi-view identity loss. Right? And I'm gonna just, because this picture is turning out to be so pretty, I'm gonna turn this into, and it wasn't clear when I originally looked at the image in their paper. This is their loss. And again, with machine learning, remember, you have, this is the neural net, but in order to train a neural net, you have to have some way of measuring the error that the neural net is producing. And so that's referred to as a loss function. Okay, the neural net is producing a result, in this case, the S&T values, and we have this way of comparing the S&T values that come out of here with the S&T values that were used to create the synthetic image. So that's a parameter loss. You can say, how close are those together? And then when you're far away, you can make changes to the neural net so that this actually works. Same thing. We now have the ability here to compare the identity of the input value that gets turned into a shape, that gets rendered, and then produce a loss function that's sort of cool. Since these are on a hypercube, you have to they call it the cosine loss function. They're basically measuring the angle between these 2 things. So, you know, the loss function, if this is your target value and you had value over here, we don't really care where it is. We want them just that angle to get closer and closer and closer. So this is the way they actually measure the loss. They call it a cosine loss, where they measure the angle between these 2 1,024 element vectors. It's easy. It's a dot product. That's what that is. Okay, so now, remember, this is the thing. Question mark. These are the values that we're trying to train. How do I train that there? Wow. Remember basic neural net 101. You have an image that goes in. You have convolutional neural network that you have set up here, or just a neural network that you have, and then it produces a value. It eventually produces just a single value there. And if I have an error in here, a loss function tells me that I'm off. There's a delta value that I want to propagate back. I have to propagate it back. I have to say, all right, how does a change out here turn into changes in the values that I'm using to run the neural net? And so I take this delta and run it through. And in order to do that running through, I need to know how the values in the neural net, so here's a weight here and a weight here, I need to know how they would change. If a change to this value produces a change on the output, then I can invert that and say, I've got the change on the output that I want, so you should change your value. I need to be able to take the derivative of this value with respect to the output. Long thing. But there's a big honking hole here, in that we have something that we've taken our 3D shape, rendered it, and created an image. So I've got a value here that I want to propagate through here, and remember, FaceNet doesn't count. I want to take values here and throw changes in those values back through and run it through there, and it will tell you what the changes to the input need to be for the output to change. So basically, I've got these things that are coming out of this. I can throw those back here and get the changes that I need to the input of the differentiable renderer that would produce a new change, the change I'm looking for. And so they have a differentiable renderer. It's super awesome. It bears discussion about this. So wanted to make sure. Ah, here we go. In contrast to previous approaches that backpropagate loss, that's the backpropagate loss, we employ a general purpose differential rasterizer based on a deforming shading model. The rasterizer produces screen space buffers containing triangle IDs and barycentric coordinates of each pixel. Per vertex attributes such as color and normals are interpolated as the pixels at the pixels using barycentric coordinates and IDs. So this renderer is actually, when it produces this image, it's actually associated with each pixel the triangle that's coming from, so that you can actually, for a change in this pixel, you can actually figure out how the triangle associated with that pixel should change. This approach allows rendering with full perspective in any lighting model that can be computed in screen space. That is important because we have to be able to differentiate this, which prevents image quality from being a bottleneck to accurate training. And the source code is for this renderer is publicly available. So the rasterization derivatives are computed for each barycentric coordinate, but not the triangle IDs. This thing and train it. Oh, so we had the very cool idea of saying, wait a sec, we know how we got here. If we could just, we have this paper and not going into some of the details, but this is the kind of the state of machine learning right now, is that we have this way of take an input and then produce an output. And notice we haven't really talked about this. And this is kind of this black box that we really haven't cared. We don't care about this. It's all this machinery around it so that it gives us the right values that we can actually train to this. And things like differentiable renderers are existing, and using existing models like FaceNet to compare identity, so clever. And the fact that FaceNet is a neural net and we can take the derivative as we go through back here, that gives us a lot of power as well. So thinking about machine learning now is more about how do you feed the beast? How do you transform the data that you're getting so that once you get your black box, you can actually train it correctly? I'm not even talking about the training of it exactly. I'm just talking about how you do this. And that's what this paper is all about too.
You also increase in the data, right?
Wow.
Every time you run a variation backwards and forwards, you're actually increasing the amount of data you have.
Of course, yes.
Because you're creating new data.
So the neat thing is, of course, we can get as many real images as we want from the internet. And then we also still have this. So notice I didn't, this pipeline is mostly there to get things going. Once we get it going, we sort of switch over, but we can still keep on going back to the synthetic images every once in a while to make sure we haven't gone off track. We're still creating actual values. So we can generate as much data as we need in order to train this as far as we want. But we're not done. We still have one more path, or two more paths to go through here. And in 5 minutes, we should be able to do this. All right, so now, I may have drawn this wrong. Well, bear with me. We're going to take our, we're going to, we're going under here. This is not nearly as clean as it was. It started out beautiful, but now it's not. So now we have our 3D morphable, what? Regressor. When I first saw this, I was like, wait, what? This is the same thing, right? It is the same thing. They actually kind of virtually duplicated the morphable model regressor, because remember, this morphable model regressor takes an identity and produces a shape. So we can also do a couple of other things. We can run the result of this, and they call this looping back. Do this again. So see, here we have the shape popping out of this. Actually compare, and they call this two things: batch distribution loss, where we compare the shape that comes out of this with this. Actually, this produces S&T, and this is the S&T that went through all this kind of stuff. So we can make sure that the results that we're producing are there. And we also do the exact same thing with a thing called loopback loss. Because time is short, we're just loss. Or we can also combine that. Now, I'm going to jump right back to the paper and describe this. And this is where I was a little less confident about this. So the batch distribution loss is to make sure that you don't go too far away. So applying the identity loss alone, if you just compare these two things, allows training to introduce biases into the decoder outputs, change the distribution. There is a way for this thing to, if all you're doing is using the identity, to work around the system. You can actually start thinking about, well, what if I start messing with, conceptually, and messing with the average shape or the average face. Remember, this all keys on having some a 3D morphable model with an average shape. And there's ways for this thing to sort of accidentally, but on purpose, work around the system so that it satisfies the loss, but produces values that you really don't want. So they go into some of the details of this. This is actually a fairly easy one where you're basically saying the values that come out of this thing should have a 0 mean and a standard deviation of 1, a variance of 1. And this little thing can make sure that this thing stays on track. It's just like a little thing that goes in there and make sure that as you're training this stuff, you don't start going off into the weeds. Same thing with the loopback loss. This is making sure that as you go through this thing, your face looks not as good. Putting these two things in there really sharpens up the face. It really snaps to it. Then you just run it. And at the end of it, what do you have? Well, everything else goes away. Remember, all this stuff goes away. All this thing, the only thing that you have is a real image that goes through FaceNet, creates an identity, and outspits 3D shape and texture for the person in a neutral pose. There's no experience going on here. The cool thing about this, though, is remember, it doesn't matter what the expressions are in the real images or in the synthetic images, because you're using FaceNet, and FaceNet is awesome. Me, whether I'm smiling or frowning or wearing glasses or whatever, we're just going and saying that should look like Doug, and that this should produce a model of Doug in the identity or in the neutral pose. So clever. Does this make sense? I started talking and then I just never stopped. But that's standard talk. This is actually, obviously I wave my hands a ton over this and I go back to the paper and I need to go back to the paper. But these two things are important. Is this actually, you understand the concept of how this thing was built? That was the main thing I wanted to get across. So clever things in here, FaceNet to identify and then put this in. And by the way, this thing works like a champ. If you look at the results they have, if you go to the end of the paper, just picture after picture, and the results are getting unbelievably good, right? And especially the texture. These guys are able to suss out the texture and the skin color, the eye color, all this detail from just anything. It's all clever stuff. All right. There will be no Chalk Talk for next week because it's July 4th and I'm not going to be here. But then there will be a Chalk Talk the week after that. I have no idea what it's going to be, but there will be one. I will be here. It'll be a Chalk Talk. It'll be fun. It probably will have something to do with machine learning, if actually